you have to learn the language of the trade. If you don't know the language of the trade, then you can't communicate with other people in the trade. You know, so if you went into a doctor's office and he called somebody in there, he says, give him a shot, give him about that much, what would you do? You turn around and walk out, right? Or he's having problems with his thingamajiggy right here. What would you do? You turn and walk out. So a lot to deal with. In fact, doctors have a problem talking to you on your level, right? So learning the language of the trade. If you're a carpenter and you don't know what a 2x4 is, some one in boards is about this big. Yeah, you wouldn't be in the business very long, right? So learning the terminology of the trade. That's what we're going to pick up some of our terms here in Chapter 2. We're going to talk about signals, digital signals, and switches. Let me try this. We're going to be able to play around with one of these devices. This is what's called an oscilloscope. Meters or multimeters are fine and dandy, but they do not show you what's there. They show you an average of what's there. So if you got any spikes, if you look at a digital meter if you look at a digital signal with a digital meter, you can't tell much unless it's moving extremely, extremely slow. So we start looking at some of these digital signals. So what an oscilloscope does, it allows us to look at voltage levels. So all a scope will measure is voltage levels. But it looks at it, what's actually there relative to time. I need to turn some information. It's got a lot more information on there than me. So this is digital. That's what we refer to as, this would technically could be called a square wave. You ever heard that term before? But a lot of digital signals are not square waves. And you can see, so one of these voltage levels represents a 1 and one of them represents a 0. Now we're going to be dealing with a type of logic we call transistor logic. Most people call it TTL, which is pretty neat because TTL, the high voltage is a 1 and 0 volts is a 0. So it makes it real easy to understand when we're dealing with TTL logic. This is actually AC, by the way. But I can do different things with this, and each one of them I have. So this is a repetitive waveform, and we're going to see non-repetitive waveforms. This is what we refer to as a clock. We use clocks all over the time, especially for synchronizing data and making sure everything's okay. So one of the things when you buy microprocessors, or if you really get into detail on your phones, is the speed of the clock that's timing the processor in your computer. And normally clock speed is interpreted to speed, right? But I can do things to this. Let's do this. Now notice I didn't change the rate of the clock. I just changed how long is high and how long is, and that's another term. So highs and lows. Y'all understand those? So what would be a high? So this would be considered a high. This right here would be considered a low. So that's another term we can use for ones and zeros, and we'll do that term a lot. So highs and lows, ones and zeros, right? We use those two terms a lot. Let's look at some of the other terms, and we'll come back to this in a minute. So this is what they're showing us. This is showing us a typical digital clock. This would be a square wave. What do you think we need to talk about a square wave? A square wave means the time for the low is the exact same time that it's high. That's what a square wave means. It don't have to appear like a square. Mine wasn't a square, so we call it square waves. All the rest of the waveforms, we would call those pulse waveforms. Technically, that would be technical. Now, of course, when we get into clocks, digital clocks, these clocks are moving at a certain rate. By the way, we call one repetition of a digital clock. We refer to this. Anybody know? So this is a repetitive waveform. How long does this go? So that would be a repetition. And then it does this. And out here we would have what? The same thing, the same thing, the same thing. And it's going to be occurring at a certain rate. Anybody know what we call one of these? We call this a cycle. So that's what a cycle is. A cycle is when it repeats itself, right? That's not a term that's unique. So you'll learn into the. By the way, all the terms we're talking about now are the same terms we use in AC. So AC runs in cycles. Are we okay? That makes sense? Now these cycles are occurring at a certain rate. Anybody know what we call the rate of the cycles? No, that's what it's measured in. It's called the frequency. So the frequency is the rate of the cycles in cycles per second. So Alabama Power generates 60 cycles per second. So that means one cycle would be exactly 1/60th of a second, as soon as I write 60 instead of 16. So this whole cycle would be 1/60th of a second. This cycle would be 1/60th of a second. I don't know why I'm trying to write 16, guys. 1/60th of a second, which would be 8.66666666 milliseconds. I did that in my head. No, I've been dealing with 60 cycles for a long time. Now, like most sciences, people who are fundamental in the evolution or of the science have the honor of getting their name given to certain things, like ohm, omega. When you get into resistance is measured in ohms, right? Voltage is measured in volts. Those are all names of people. So we came out with a term called Hertz, which stands for cycles per second. So 60 hertz, we will hear hertz used. So even in processors, you've been heard about, I'm running at 60 gigahertz, right? You understand that? I think they even give a lot of times they give bandwidth on the network in hertz. Now the time it takes for one cycle, we refer to this as the period. So I'm doing this kind of like a lot of people do math formulas. They put, and somebody's going to do that in this class. We're going to learn, we're going to get an introduction to something called Boolean algebra. People get it reversed. So that means if this was 60 hertz, that means each cycle would be 1/60th of a second. So the period, which we usually abbreviate with a lowercase t, would be equal to 18.7 milliseconds. And y'all all had intro, so y'all got engineer notation. It's actually 18.66666666. So if you take what we call the reciprocal, which is 1 over the number, you should come up. Everybody okay so far? And these are terms that you've heard a lot. I'm sure you've heard hertz somewhere down the line. Even when you talk about processors, they talk about the speed. They talk about hertz. How fast we move information, they talk about hertz. but it actually stands for cycles per second. Now the period, we need to understand that too, because especially when we're using a piece of equipment called, especially if we use what we call an analog oscilloscope, which are the cheapest ones. This oscilloscope we got here, this is a digital oscilloscope, which means it's a computer. So it'll do a lot of things too for us that an analog scope won't. But if you go to work somewhere, odds are they won't have an analog scope because it's a lot cheaper. You get more features and cheaper, right? Analog scopes measure time. They don't measure frequency. So if they measure time, so let's say about this. So we got this thing in life we call the reciprocal. What is the reciprocal? Well, the reciprocal is this right here. Or is any number raised to the minus 1. If you raise any number to the minus 1, it will be divided into. Okay, you'll understand that. And this is so popular by getting the inverse or the opposite of. The opposite of. So that's what a reciprocal is. It's the opposite of. So if I put the reciprocal of 2, it's going to give me 0.5. Well, 0.5 is the opposite of what? 2. And that's why when we go over to the other side, this holds a weight of 2 to the 0. This holds a weight of 2 to the minus 1. Well, if it's to the minus 1, it's what? It's the reciprocal, right? Which would give me what? 1/2 of 0.5. So that means I knew that if it's 60 cycles per second, then if it's 60 cycles per second, then I know that each cycle would be 1/60th of a second. So if the frequency goes up, what's going to happen to the period? So let's say I double the frequency. So if I double the frequency, let's say I go to 120 cycles per second. Now that means each cycle is going to be 1/120th, right? So if I double the frequency, then what happened to the period? Didn't double, can't double. Think about it like you doing a task. I'm doing 10 things in an hour. Okay, so think about the 10 things you're doing in an hour as cycles. Don't understand that. So that means if I'm doing 10 things in an hour, it would take one, and each one of them are equally spaced, then one of them would take me 1/10 of a second. 1/10 of an hour. Well, now all of a sudden I'm doing 100 things per hour. So you're saying the time I'm taking to do each one of them is going to go up? No, now each one of them would be 1/100th of a second, right? You understand? So if frequency goes up, the time for the period goes down. And they are inversely proportional, exactly inversely proportional. So if I go from 60 and I double it and go to 120, my period goes to 1/120. And hopefully you know if the bottom number goes up, the time's going to go down. So that means if I double the frequency, the period half. Which means I can take the reciprocal of the frequency and it will give me the period. So the period is the inverse of the frequency. Inverse. So if I know the period, how can I find the frequency? Take the reciprocal of that, right? So F is equal to 1/T, and of course T would be equal to 1/F. They're inverse of each other. So that means if I've got an oscilloscope that measures time, I can calculate the frequency by taking the time for the period and then taking the reciprocal. Now digital scopes, you can tell it to give you the period because they're computers. And it's nothing but math anyway. And that's all this information that it's giving me on my scope screen up here. I need to turn that off. I have to go back and figure out this. So normally when we measure signals with an oscilloscope, we measure time, and then I convert it to frequency, right? Everybody okay there? Any questions? Yes, no? Indifferent? Have I lost anybody? Where did I lose you? So you've heard the term cycle, right? Okay. So, but now you know what it means. What's cycle? one repetition of a repetitive waveform. So when we say repetitive waveform, how long would this go on? How long is 60 cycles being placed on these lights right here? Until you do what? Until the power fails or you turn them off. So what you got to understand is that when this cycle ends, this cycle does what? It's like 12 midnight. What is 12 midnight? End of one day and the start of each other. So we go in cycles, right? Then we have what we call frequency. What's the frequency? Well, it's how fast the cycles are occurring, right? You understand? How fast do they occur? So a frequency would be like a year, 365 days a year, right? What would a cycle be? A cycle would be one day, right? So 1/356 of a year, 1/365th of a year, right? You understand that? So that's what a day would be relative to a year. And then the period would be 24 hours, right? So that's our period, 24 hours. So the frequency would be, so the frequency would be like the days in a year. The period would be what? How long a day is. That makes sense? Huh? It's hours in a day. Of course, we're not going to go to seconds. But the 24, okay, so frequency would be what? 365 in a year. Then a day would be one cycle, and then the period would be the time for one cycle, which would be what? 24. And then 12 midnight. What's 12 midnight? It's the start of this day. It's the end of this day. But it's also what? The start of the next cycle. So that means the end of this cycle is the start of that. So when this one's going down, if this starts on this edge right here, which we call the what? What do you think we call it? The falling edge. Does that make sense? So if this one starts on the falling edge, it's going to end on the falling edge. This would be the falling edge of the next cycle, and these go on forever. As long as this computer's right here is turning on, if I was to get the oscilloscope, this oscilloscope would measure. This is only a 25 megahertz scope, but we got a 100 megahertz scope in there that still wouldn't measure. A lot of our scopes now, a lot of these microprocessors are running up in the gigahertz range. So okay, that happy? So we talked about period, we talked about frequency, and we know now that frequency is the reciprocal of the period, and then of course the period is the reciprocal of the frequency. Are you okay there? Good. Everybody okay with engineer notation? Y'all learned that in D6. Well, you learned it in intro. You should have learned engineer notation. And we do this a lot. Now, we don't go around and say, we're going to expect this out of you, right? We're going to expect you to use engineering notation in the classes that you take here to get you used to using it. The more you use a language, the better you get at it. I've known people that's learned languages because they move them into a different country. They don't take any classes, but they just slowly pick up phrases and learn how to speak the language. Have you ever known anybody like that? The English language is a hard language to learn. Huh? What? Which one? No, that's not the right abbreviation. I understand. Yeah, that's wrong. We can't, and you can see it's is this in your book like that? Table 2 one? Is it right? Is it? Yeah. So this is PowerPoint. Yeah, we can't have the same abbreviation for two different units. I hadn't noticed that before. Yeah, but you're right. That would be the Greek for micro. And notice K is a lowercase a. A lot of people put an uppercase, and that's true. It's lowercase K. Assume you use lowercase K. Yes. Oh, I should. Are we okay on these? We'll use these. We can send information 2 different ways. We can send it in what we call serial, and we can send it in parallel. What would you think the advantage of serial would be? What do you think serial means? Well, serial means 1 bit at a time. So if I'm sending 1,000 bytes of 1,000 bits of data serially, I'm sending them one after the other. Parallel means every bit's got their own wire, own conductor. Every bit has at least one conductor, usually 2. We'll talk about that in a minute. So this would be an example of serial. We have 2 methods we can use. We can use synchronous serial. So synchronous serial means we're going to send this with some clock. And what we do is we only read the information. We only read the information on an edge of the clock. So let's say we're timing on this edge right here, the rising edge. So what would this receiver see? Well, what we would do is we would come up here, and what would it see? It would see a 1. What would it see right here? A 0. What would it see right here? A 0. If I'm going to send multiple bits, I can't go 0, 1, 0, 1, 0, 1. I might have to go 0, 0, 0, 0. Well, we have to say, okay, you know, so this is actually 2 zeros, even though y'all understand what we're saying. But we have no problem because we're only reading it on what? On the edges. So this device over here will see this as 2 zeros, but I have to be able to do something like this because I have the patterns I'm sending are going to be, you know, if I'm sending the ASCII code for a letter R, it's not going to be at 10 10 10. It's going to be 1. Y'all understand what I'm saying? So what would it see right here? It would see this as a 1, right? What would it see this as? It would see this as a 1. What would it see this as? 0. What did it see that at? It see it as a 1. And we call this synchronous. Now notice how many wires it has. So this would be like me throwing stuff on here, one digit at a time. 1 digit at a time. And what you're doing is that you're not listening, all you're doing, and 1 digit at a time, that's what serial is. So that means I would come up here and I would do this, because we can only have 1 polarity on a wire at a time. Well, what I would do is y'all all sitting back there like this, and once I get a character up there, I go beep, and you do what? You open your eyes. And then what do? Then you close them. And then I go beep, and then you open your eyes. Right? You understand? So that way, that right there would be 2 zeros. Right? Y'all understand that? So synchronous is extremely fast. We can send this at extremely fast rate, but it takes more wires. It takes at least 3 if I'm going one direction. If I'm going 2 directions, it would take 6, right? You understand that? Because you would have to send your synchronizing information from the other direction. Called synchronous serial. Is this what Ethernet uses? Heck no. You can think about the number of extra wires that would be required to send information 2 directions at the same time, right? You understand that? We'll talk about different terminologies here in a minute. So what we do is we use something called asynchronous serial. This is the predominant method of sending serial data. Asynchronous means, so synchronous means with a clock. So everything is timed with a clock. So inside this processor, it is synchronous data. And that's when they specify the speed. When you buy a processor, one of the big things is the speed. And that's the speed of the clock. That clock is doing what? Time in the data transfer. That's what it is. But as soon as it leaves out this Ethernet wire and goes up there and goes over that box over there, now it's asynchronous serial. Why asynchronous serial? It just saves so much money. How in the world can I do this? How can I represent ones and zeros? Well, what we do is we send it at a precise rate. It's called the baud rate or bits per second. So when we looked at that the other day, when it said 9600 baud, it means it was sending 9600 bits per second. So it means it was sending the bits out every 1/9600th of a second. Your receiver is going to receive at the same baud. So one thing that's got to be negotiated is the bit rate. If the transmitter and the receiver transmit and receive at exactly the same rate, then that would be like me and you. I've got a time on mine. I'm not beeping anymore, but what you've got is you're beeping in your head. Or you've got a watch or something. It has to be pretty precise, right? And I'm up here, and we're synchronized, and I'm sending out 1 bit per second. I change it up here, and you read it 1 bit per second, but I don't tell you when to read it. You are doing your own timing. And this is called asynchronous. Right off the bat, we save 1 wire. Copper costs a lot of money. You think about how much copper. Before we went to Wi-Fi, y'all see that sucker up there? That's a switch up there at the top. It's a network switch, which basically takes a single cable and routes it all over the place. It costs like $250,000 the first time to wire the college for this network. And it's 2 directions, so that's at least 4 wires. We got to use 4 wires because we're trying to send information 2 directions at the same time, which we'll talk about what that is in a minute. So asynchronous serial. So this is it, guys. The Ethernet uses asynchronous serial. The whole internet is asynchronous serial. And why serial? Because you say, well, we can send it faster if we did parallel, but it would be extremely expensive. Extremely expensive. Extremely expensive. And what we find out is that a lot of times you don't need to go any faster than the technology you're using. So for years, hard drives were parallel. We called it ATA, which was Advanced Technology Accessory. But it got a new name. They call it parallel ATA because what they did is they switched over to serial. Y'all ever heard of serial ATA? SATA? But as long as the technology can be faster than the hardware, you're okay. When they came out with the Phantom F4, they put 2 big old jet engines in there, and they never could run those engines at 100% because the airframe couldn't handle the speed. The F4 would go in excess of Mach 2. Y'all remember the F4? It had 2 big jet engines in there, and they never could run that sucker full speed. So that was basically, it'd be like you going out and buying a 1,000 horsepower motor and putting it in a Volkswagen chassis. I mean, if you tried to go as fast as that motor could send you, the car would just tear apart. So the ultimate goal, if I'm a drag racer, my ultimate goal is to beat everybody out completely. Right, you understand? If I go out and build a car that's going to cost me $1 million, I'm going to beat everybody, but I'm going a lot faster than I need to go. That makes sense. So we've came out with some other technologies we'll look at in a minute. The problem we have with this became known as single-ended interface, which means we have one wire that handles it. We call it the data wire, and then one wire would be considered to be the deterrent. It's usually referenced to earth ground. Now, the problem we had with this, using this single-ended interface, is that y'all know what magnets do when a magnetic field passes through a wire. You know what it does? It tries to induce voltage. And how much voltage you induce would depend on the current carrying capabilities that you're sending it through. Guys, we're sending ones and zeros. How much current are we going to use for those ones and zeros? Almost none. Practically unexistent, right? Y'all understand that? Which means these guys are extremely accessible to electromagnetic interference. We call it EMI. So what was happening to us is a magnetic field would pop in here, and it would induce a voltage into that, and it would give us problems. So single-ended is limited to the length. So our serial interfaces were really, really limited to as far as we could go. Single-ended interfaces, like the maximum for printer cables were 15 feet. That was the maximum you're supposed to run. So they can guarantee maintain in ones and zeros over 15 feet. If you got it over there, it was no longer guaranteed. Huh? Well, shielded cable costs so much more. You're right. We could use shielded cable, and we still do, but compare unshielded cable with shielded cable. And what we're trying to do is we're trying to send this information extremely, extremely fast. One of the things they did do is they doubled up on the grounds. Or what they did is for a long time you ran one data wire, one ground wire, one data wire, one ground wire. So the conductor over here could not induce a voltage over into the next data wire. But now we're really, really up and up. I can show y'all some of the cables, some of the flat cables we use to interface our hard drives and stuff like that. So what they wanted to do was they came up with a technique where we don't use ground. We stay away from ground. And what they did is they came up with a technique called differential interface. What we do is we use two wires. One of them they call plus and one of them they call minus, but that's just a designator. It's not one of them is negative, it's not one of them is positive. And what they do is they send the two signals 180 degrees out of phase, or just opposite of each other. So notice when this is the mirror image of that. Now, what they do this for is they developed an amplifier, and unfortunately we don't have time to get into it in this class, but it's called a differential amplifier. And it's a really neat circuit that only passes signals that are moving in opposite directions. It only lets signals moving in opposite directions come through. Any signals that are moving in the same direction are rejected. They call it common mode rejection ratio, if you ever read that. So what happens, these wires are in direct contact with each other. In fact, we use what we call twisted pair wire. You ever seen that? So these two wires are together. They're routed together. They're twisted together. And when the magnetic field comes through here, it would induce a voltage here and it would induce a voltage there. But if the magnetic field is going in the same direction, it would induce the same voltage in both wires. And these wires, these are moving in the same direction. So what would this amplifier do? It would reject what we call common mode signals and pass differential signals. That's what a differential amplifier does. And guys, this right here reinvented serial communication. That's why we have Ethernet. That's why we have wired Ethernet. It's not shielded cable. It is unshielded. We call it UTP cable, unshielded twisted pair. We can run that wire 100 meters, 330 feet through just about anything. We just can't carry it outside because of lightning. That's not because of common mode. It said if lightning got into one of the cables, it would blow up these differential amplifiers. So normally when we go here, we're supposed to use fiber optics. So we got fiber optic cable lines from here to the buildings. Differential. Serial ATA uses differential. Ethernet uses differential. USB uses differential. And this is basically serial ATA. So what they did is they can run extremely fast speeds because now the wires won't interfere with each other. So we went from parallel ATA on our mass storage devices over to serial ATA. Now our hard drives are all serial ATA, which instead of having this big old flat cable, which is about that big, we got a little old tiny flat cable. We can route them. It makes airflow inside our computers so much easier. And it's revolutionized serial communication. It's differential. So parallel was flat wiping out. Parallel for speed and serial for cost. Now I think we're on the serial ATA version almost 6. I think it's 6 gigabits per second that interface could handle. Hot swap interface, you know what a hot swap means? It means you can plug and unplug devices without turning them off, which is super cool. So USB is a hot swap. So what can you do on that? What can you do with these USB sticks? Yeah, all you got to do is just make sure you're not writing to them when you pull it out. So most operating systems give you a little eject thing, which basically, if you're writing to them, it'll wait till the write overs before it lets you eject. But you don't have, I mean, if you're not writing anything to them, you don't have to, y'all know y'all don't have to do that, right? So you can pull them suckers out, you can push them in, no problem. If you ever looked at the pins, you'd say the two data pins are inside and the power pins are outside. So the data pins break before the power pins. Serial ATA. Differential interface. So now we refer to this as single-ended. So if you ever hear single-ended, that means it's a data wire plus a ground. Differential means we don't use ground, but we always have a difference of potential, right? So to recognize voltages, we have to have a difference of potential, but we always have a difference of potential, because when this one's high, this is what low, and when this one is low, this one right here is high. So we always have a current path. It's just that we don't use ground anymore, and we use differential amplifiers. Beautiful interface. And these guys right here are neat. If you take the second electronics course, we get into how differential amplifiers work and all that kind of stuff. But all these guys, all they do is pass the what? They pass signals moving in opposite directions. They don't pass signals moving in what? Same direction. Electromagnetic interference will move in what? Same direction. So these are all our ports that use asynchronous serial. Most of them are, these are serial. The old COM ports, all your USB standards. But we're now on version USB 3.0, which can get us up to 5 gigabits per second. But all these are downwardly compatible. So USB 1.0 could do 5 and it could do 12. USB 2.0 could do 5, it could do 12, and they added what? 480 megabits per second. USB 3.0, which is the version we're on now, I think they're working on 4, or they might have 4 out already, do they? It'll do what? It'll do 5, it'll do 12, it'll do 480, and it'll get all the way up to 5.5 gigabits per second. And it's supposed to be blue, by the way. I don't know if you noticed the little flat thing in there. So if you got one that's blue, that's USB 3. If you got one that's black or white, it's USB 2 or 1, right? And it's downwardly compatible, so that means I can take a USB peripheral. These guys come up here and they handshake with each other and figure out which the maximum speed they can communicate with, and that's what they can make. Pretty neat. Serial ATA. So this is serial, guys. 6 gigabits per second on a hard drive. Pretty good speed, right? Whether they got a new version out, I don't know. I need to go back and check. This is the predominant interface now for your hard drives, for your CD-ROMs. Even those DVD players use this. What's nice about the serial ATA is a hot swap technology, so it's moved us where we can buy devices and plug them in and take them out. That's what's so neat about this array up here. If a hard drive fails, what can I do? I don't have to turn it off. I can just do what? Open it up, pop it out, put a new hard drive in there, close it up, and then it automatically rebuilds the new drive. What time is it? Time for a break. These are some of the standards that use serial. V90, we're still making. These are modems. The ISDN, I've heard of ISDN. T1, T2, T3. These are connections for telephone company provides for internet use. USB, I know y'all have heard of USB. Ethernet, I know y'all have heard of Ethernet. 10BASE-T. These are different versions of wired Ethernet. 10BASE-T uses what they call baseband. Y'all know what baseband is? Y'all know what the difference between baseband and broadband is? Y'all know? Baseband is a technique where you have this is what Ethernet is, and that's what I talked about a while ago, where you put a packet on, then you come off, and then you put a packet on, you come off. So there's only one person There's only one device that will be on your subnet at a time, and that's baseband. But when they are on it, they get the speed of the network. So if I'm using 100 megabit Ethernet and I'm the only one on that, then I get 100 megabits. Broadband, what we do is we take all the signals and we place them on something called a carrier. And what we can do with broadband is we can have multiple devices on the network at the same time, but they're sharing the bandwidth. So it means if I got a bandwidth of 10 megahertz and it's baseband, when I'm on the network, I get 10 megahertz. If it was broadband and there's 5 people on there, then we get 2 megahertz apiece. And you're limited to the number you have on there. So broadband, you're more likely to get on the network faster, but when you're on there, your data's slower. Baseband, you gotta wait, right, on the network, but when you're on there, you get full speed. So baseband, it's basically different, but if you get on a baseband network that's got nobody on it, you're gonna fly. If you're on a broadband network, then you get a bandwidth, period. Well, yes and no. Ethernet, if you got a wireless router or anything like that, Wi-Fi, that's baseband. So Ethernet is baseband. But you got to imagine, you're in your house, you got maybe 15 devices, and how often are they on the network? So is this computer right here on the network? No, it's not on the network. It's only on the network when I try to transfer something. So if I go out and bring up Internet Explorer, it's there long enough to load down that page, and then I'm not on it anymore, right? You understand? So you're only on there when you're transferring data. That's the only time you are on the network is when you're transferring data. Now you're coupled to it, right? You understand, but you're not putting data on. So baseband, if you got an empty network and you're on baseband, it's gonna scream. If you're on broadband and you got 5 megahertz worth of bandwidth, and you got 5 megahertz of bandwidth if you're the only person in the world out there, right? You understand? But and usually the company charges you for bandwidth.
Yeah, but whatever the speed they're telling you, they're not providing the same speed.
Yeah, it's usually a download speed, not upload. If you got upload is is usually limited. Download is pretty fast. Yeah.
But even download is also, even the AT&T, what they tell you, oh, this speed, but if you check your speed or go on Google and check your speed,
well,
you're not getting that speed.
Yeah, and they vary the bandwidth, so that's a problem. You pay for so much bandwidth, and you don't get it.
Yeah.
So y'all know that now bandwidth makes sense, right? Because that's the range that you can go. So PBHP, this is a 10 megahertz baseband. 100 megabits, and then of course we're at gigabit, what they call gigabit Ethernet right now. And then of course your cable is serial, and then DSL. I know you've heard DSL. That's one of the companies talks about. That's a wired system. It's a telephone system. The old COM ports use single-ended interface. These guys here could only run up to 115 kilobits at 50 feet on the COM ports, which was good. And then all your USB standards uses differential interface, and serial ATA uses differential. Then we got parallel. So here we have a separate electrical conductor for each bit. Now the big advantage of this, the biggest disadvantage of parallel is that right there. It's what? Very expensive. Because you got one wire per bit. So the predominant way we send information is serial, strictly because of the cost. Very fast. Everything inside your computer is parallel. I don't know except I put except serial ATA. Serial ATA is a peripheral, right? You understand? Centronics port was parallel, and something called SCSI, which is small computer system interface. SCSI is still pretty popular in extremely big servers. And this is parallel. The analogy I like to use is like, if we had a single lane road going from here to Birmingham, everybody would eventually get to Birmingham, and everybody would eventually get to Bethel, right? Understand? but it would take what? Be very cheap to build one road, right? But what do we do to get the cars to move faster? We go to parallel. We call them lanes. So most of our interstates are multiple lane roads for one reason. To do what? To make it faster. That's exactly why we do multiple lane roads. But it's more expensive. So an 8-lane interstate is a lot more expensive than running a 2-lane road.
That's what we have in front.
Or a one-way road, yeah.
Highway 85. Go all the time.
Yeah. Especially when the ball game's over.
Yeah, they have
right there.
Saturday, Falcon is playing.
So parallel, this is what they use inside your computer. Probably this is what they use inside your cell phone. The OLPT ports, which were, by the way, the LPT used single-ended interface, and so what the problem the LPT or the parallel ports had in the old computers is that it was single-ended, which means it ran aground, right? You understand that? Ran aground. SCSI, this is a parallel interface, and then, by the way, what we're supposed to do is, if we use a lowercase b, that stands for bits per second. If we use an uppercase b, that's supposed to stand for bytes per second. Most of your serial interfaces should be given in bits per second. Your parallel should be given in bytes per second. So this is where we're going to lay off tonight. We're going to go ahead and give you out the lab procedures. Again, the first lab form and then your first lab. The first lab we're going to do is not a hardware lab, it's a software lab. And it's going to be the programs that, a program that I wrote. Don't get too impressed. So these are the lab procedures. I wrote them back. No, I didn't. That's not. That's the. That's the road. So we'll start right here, next class. It goes past